Hello children, in today's class we will be discussing the full chapter of work power energy. So this is a chapter 2 in ICSE class 10. Dear children, in this chapter we will be having a main 3 units. In a unit A we will be discussing work, types of work and the factors on which work depends, power on which factor does it depend, then energy and the special units. Now, whereas in unit B, mainly we will be discussing about the types of mechanical energy. That is potential energy, how to calculate the gravitational potential energy. Then we will be discussing about the kinetic energy, expression for kinetic energy. Mainly we will be talking about work energy theorem. Children, it's very important. And one more point also we will be discussing in a unit B. That is how kinetic energy is related to the linear momentum. Children, based on the relation between kinetic energy and linear momentum, we will be having a number of numericals which are very important for examination point of view. Whereas in unit C, only the single point which we will be discussing, that is what? Law of conservation of energy. We have knowledge about the law of conservation of energy, but especially in 10th class, the mathematical verification of law of conservation of energy which we are going to discuss with the help of freely falling body, and also we can understand this law of conservation of energy with the help of simple pendulum. So these are the main topics which we are going to study and we are going to cover in this chapter. So children, first before going to start our discussion, children, the two important words which we should know very well to understand the work. So what is that? The first word, of course, we all are very familiar with that word, and moreover, this is the word, I mean, if I can say this word, you can recall the chapter 1. Yes, that is what actually force. So children, can you recall once again what actually force is? Come on, which we discussed very clearly. So what is a force, children? It is an external cause which can change the shape of an object, position, size, direction of an object. And here force is a vector quantity. Force is a vector quantity, and even we all know about its units also. The SI unit of force is Newton, whereas the CGS unit is Dyne. Children, how Newton and Dyne are related? Just recall once again. Yes, 1 Newton is equal to 10 power 5 dynes. So this is about actually force. Next, children, what is a displacement? What is displacement? So about the displacement, we had discussion in class 9th, the chapter called motion in one dimension. Children, what is the displacement? The shortest length between initial point and a final point in a particular direction is called what actually? Displacement. It's called what actually? Displacement. Okay, fine. So displacement also vector quantity like force. It is also vector quantity. Its SI units are meter and its CGS units are centimeter. So children, this is a, these two words are very important. Of course, we all know very well about what actually force and what actually displacement. So once again, before going to learn about what actually work and its units, children, so we should have this minimum knowledge. Okay children, fine. It's better you can just make a note of it. What is actually force, units, displacement and units. Now children, let us see what actually work is. Children, can you think about what actually work is? So since what we can say, the moment when we will get up to the moment when we go to bed, we will come across with many works actually. Yes or no? But dear children, what we can say means whatever we feel a work is different, what actually we discuss scientifically, the work is different. You may get one doubt, sir, how in terms of science the work differ from our daily life? Yes, that we'll discuss. After discussing about the work, units and everything, yes, the factors will be there, we will be discussing. Really whatever we are doing, can we say that it's actually a work done or not? If not, what we can say work is done in our scientific life, not in a what we can say personal life. I'm talking about the purely science. So scientifically, how can we define work? When we can say that work is done, what are the units, on which factors work done depends, when you can say that work is positive, when we can say that work done is a negative, and when we can say that work done is 0. So first children, let us discuss about work. What is work? For suppose children, let us take, here is an object. Here is object is placed at a point A, let us say. Let us suppose it initially it is at rest. And so that, and here let a force F is acting on a body which is placed at a point A. And here what happened, this body is displaced. Try to understand. The body is displaced from A to B in the direction of applied force. Okay. So let us assume that the displacement is S. The displacement is S. Then we can say that work is done. Come on, let us define work done, children. So here work is said to be done when a force displaces the body in the direction of applied force. Body must be displaced, or we can say that the point where the force is applied must be displaced in the direction of applied force. Then we can say that work is done. So mathematically, children, we can say work is equal to force into displacement. Work is force into displacement. Children, here only some students will have a doubt, even especially when you go to the 11th class, there you will be discussing about, we will be learning about scalars and vectors, very, very important. Here we have taken only magnitude of force, magnitude of displacement. If you can take a force as a vector, displacement a vector, then you cannot write like this form. Then how to write? Let me tell you here. For example, if you can take a force as a vector quantity and a displacement as a vector quantity, then children, the dot product is equal to the actually work done. It's very, very, very important. Very means very much important. Even we will be learning in the the properties of vectors. One of the important properties that the dot product between two vectors is always scalar. It's very, very important, children. What is that? The dot product between two vectors is always scalar. So here we can say that here work is a scalar quantity. Work is a scalar quantity. Does not depend on direction. Work doesn't depend on direction. You cannot say that I will do 10 joules work in east direction. I will do like 100 joules work in a west direction. You can't say that. Just we only can measure. We only will talk about the what we can say, only magnitude. Okay, now so this is what actually mathematically we can define a work. Now let us see the units, children. So first let us see SI units. In SI system, children, force is measured in Newton, displacement is measured in meters. Obviously work is measured Newton meter. It's very, very important, Newton meter. Children, this Newton meter only given a special name. What is that? It is joule. This Newton meter is given a special name called joule. And here, what are the CGS units? Let us see. CGS units. In CGS system, force is measured in dyne. Children, as we have learned already, there is no shortcut for a dyne. There is no symbol. Let us write dyne completely. And here, displacement is measured in centimeter. Obviously, work units are dyne centimeters. This dyne centimeter only given a special name called what? Actually erg. So now onwards, children, in exam, if it is asked what is a SI unit of work, what we should write? We should write as a joule. What is a CGS unit of work, children? We can write as a erg. And in examination point of view, it is asked to derive the relationship between joule and erg. It's very, very important. How joule is related to the erg is very important. Let us discuss, children. Before that, we should know the relation this. 1 Newton is equal to 10 power 5 dynes, whereas 1 meter is equal to 10 square centimeter. So now, children, let us see. 1 joule is equal to, 1 joule is what actually? Newton meter. Newton, 1 Newton meter. So in the place of Newton, children, can we substitute 10 power 5 dyne? Of course we can. That is 10 power 5 dyne into, in the place of meter, we can write 10 square centimeter. So it is going to be, children, 10 power 5 into 10 power 2 is how much? 10 power 7. It is 10 power 7 dyne centimeter. But we know very well What is 9 centimeter, children? 9 centimeter is called as erg. So here 1 joule is equal to 10 power 7 erg. So children, this is a very important relation. Or we also can write 1 erg is equal to 10 power minus 7 joule, children. Either of one you can write. Okay. So when we are solving the numericals, this relation is very important. Even in exam also directly they will ask, what is a SI unit of work? How is it related to its CGS unit? So the SI unit is joule. 1 joule is equal to 10 power 7 erg. Okay children, just copy it. Fine children. Even in exam sometimes they will ask us to define the SI unit of work, and even they will ask us to define the CGS unit of work also. I mean what is a joule, what is a erg is a very important examination point of view. For suppose, let us see here. What is a joule we will discuss. What is joule? This definition is very important. For suppose children, here an object is placed on this body, children, a force of 1 Newton. How much force is acting? 1 Newton force is acting, children. Then obviously what will happen? The body will be displaced. If this body is displaced by 1 meter, this body is displaced by 1 meter. I mean what? A force of 1 Newton displaces the body by 1 meter. Then work is said to be done 1 joule. It's very important. I mean what, children? If a force of 1 Newton is acting on a body so that body is displaced by 1 meter, then work is said to be done, children, 1 joule. Very important. Similarly, how to define erg, children? How to define erg? Or when you can say that work done is equal to 1 erg. Now let us take similarly. Let us take an object is here. On this object, children, a force of 1 dyne is acting, children. It's very important. Now how much force is acting? 1 dyne force is acting. So whenever a force acts on a body, here what will happen? Body will be displaced. If this body is displaced by 1 centimeter, here you may get one doubt. Sir, 1 meter means you are writing showing very small length. Here centimeter means you are showing big length. Children, it's not that exactly. It's 1 meter, 1 centimeter. For sake of just our convenience only, I am making it. You no need to think that much about the diagram. Clear? So body is displaced 1 centimeter. Which means what, children? If the force of 1 dyne displaces the body by 1 centimeter, then work is said to be done 1 erg. That is what, children? If a force of 1 dyne, displaces the body 1 centimeter in the direction of force applied, then work is equal to the erg. So children, this is how actually we can define. It's very important. Children, let us recall. What is a joule, children? When you consider work done is 1 joule. If force of 1 Newton displaces the body by 1 meter. Whereas to define the erg, children, the force of 1 dyne should displace the body by 1 centimeter. Is that clear? Yes, fine. So here one more very important thing, children. So do you think that every time body is displaced in the direction of opposite force only? Come on, think, children. Is it possible? Come on, think. So children, it's very important. It is not compulsory that always body must be displaced in the direction of applied force. Children, W is equal to F into S. Again, I repeat once again, children. This, whatever we discuss, W is equal to F into S. Especially, children, this formula is used only when a body is displaced in the direction of applied force. Then you may get one doubt. Sir, what happens when a body is not displaced in the direction of applied force? First, let us think. Do we have any situation where body is not displaced in the direction of applied force? Of course, many we have. Come on, children. Think once. Do you have any idea? Children, if you have any idea about the bodies which are not moving in the direction of applied force, what you have to do? Just try to comment. Just so that I will go through it. If any new example is there, definitely I will try to learn it. Okay? Come on. Think about it. So, do we have any situation where bodies are not displaced in the direction of applied force? Yes, we have. Children, trolley bag. Look at here. For example, here is, oh, trolley bag I said, na? So somewhere out, okay, let us say it's a trolley bag. Here some wheels will be there. Clear? So this is what actually that where we'll be holding. We'll be applying force actually like this. But do you think that this trolley bag will be going in this direction? No. So the body will be moving in this direction. The body. I mean what here? Force and displacement means body is not displaced in the applied force, in the direction of applied force. I'll tell you one more thing. So children, so I think right now the IPL craze is going. Okay, fine. So during a break time, what will happen generally? They'll be cleaning the pitch with a roller will be there. So this, like this will be there. Okay. So here they'll be holding like this actually, this, and they'll be applying the force in this direction. But it won't go in this direction, children. So it will go in a horizontally. So if you can see these examples where what is happening, there will be some angle. There will be some angle between the force and displacement. Then here we will get a doubt to our mind. Okay, we have learned, till now we have learned when a body is displaced in the direction of applied force, we have formula that is W is equal to F into S. That is fine. But here what is happening? Body is not displaced in the direction of applied force. There will be an angle between force and displacement. Children, in this case, how to calculate the work done? How to calculate the work done? How to calculate the work done? Now let us see here. Means now we will be discussing, children. We are going to calculate work when there is a angle. Children, it's very, very important. There is an angle. There is an angle. Suppose let us say theta between force and displacement. Force and displacement. How to calculate? This is a very, very, very important. Hope I am clear. Fine. So let us take example, children. Let us take some inclination. See, children, actually this concept we can explain by using trigonometric ratio concept directly, and even when you go to the intermediate first year, children, there we will be discussing about the resolution of vector concept. So we can write the expression for a work done when there is an angle theta between force and displacement by using resolution of vector concept, and even by using the just trigonometric ratio concept also we can write the expression. Let us see. So for suppose, children, here is some inclination. Let us say here is some inclination. So here is horizontal surface. So that this is an angle theta. Let us say this point is A, this point is B for suppose. Okay, na? And here one object is there. Let us say here is an object is there. Okay, and here, children, a force F is acting. Force F is acting. So as it is inclination, obviously body won't go like this. Body will go in this direction. So body will be going in this direction. Finally, let us say the body has reached this point B. This point B. Let us say this displacement is S. In this case, how to calculate? In this case, how to calculate is very, very important. Come on, look at here. So from this point B, children, let us make a projection that is perpendicular line to the horizontal surface, and let us name it as a C. Let us name it as C. But thing is that, children, we know force and body is going A to B, but when you take a displacement, that is what, children, here work done we should take as a force into displacement is what? A to C. AC we should take, that is AC. But AC is not known, children. AC is not known. Then how to calculate? So it is a right angle triangle. In this, let us define cos theta. Cos theta is equal to, children, adjacent side AC by AB is a hypotenuse, right? AB is a hypotenuse. From this, AC is equal to AB into cos theta. But AB is known. AB is how much? S. AB is what? S. That is S cos theta. So AC is S cos theta. Let us substitute this. That is, we got W is equal to force into S cos theta. This also can be written W is equal to F S cos theta. It's a very, very, very. Here F and S, children, the magnitude of force, S is the magnitude of displacement. What is the theta? Theta is a angle between force and displacement. So children, come on. So then how to write the expression for a work when there is an angle between force and displacement? Children, work is equal to, again I repeat, it's very important, force into displacement component, or work is equal to force component into displacement. Even of course we also can write in terms of force component also, but still we will get the same expression. So examination point of view, they don't ask you to derive this expression, but just remembering this expression is very important. W is equal to Fs cos theta. Hope I am clear, children. Fine. This you have to remember. That is what work is equal to Fs cos theta. When we have to use this formula? When there is some angle between force and displacement. Again I am telling you, children, it is not compulsory that body must be displaced always in the direction of applied force. Sometimes body may not be displaced in the direction of applied force. Then we have to use this expression to calculate the work done. That is W is equal to Fs cos theta. Clear? Fine. Now we see the factors on which work depends. Children, examination point of view, these are very important. So here work depends on, very important. Now we are going to discuss work. Work depends on mainly three factors, children. Work depends on mainly three factors. Okay, then? First one, look at here. First one, look at it. It's very important. Very important. For suppose here means first one is what actually? Force. Work depends on force. I mean what? If more force is applied, then obviously body will be displaced more. Then obviously the work done will be more. Am I clear? Fine. And the second one is displacement. It is what actually? Second factor is displacement. Second factor is displacement. Even the work done also depends on displacement. The third factor, children, very important. That is what actually? Angle between force and displacement. The angle between force and displacement also very important. Here I am not discussing in detail, children, because as we have planned to discuss entire chapter in a single video. So if you need in detail discussion about the factors and how work depends on all these things, links will be given in description where each and every topic is discussed in detail. You kindly go through it if you want in detail discussion about it. Okay, so this video is mainly for what? A revision purpose. It is a very useful to us. Okay, fine. So children, this is what actually work and a work expression when a body is displaced in the direction of applied force, and even work expression which we discussed when a body is not displaced in the direction of applied force. And here work depends on mainly three factors, that is force, displacement and angle between force and displacement. Is that clear? Fine. Now children, we will discuss the types of work done. That is when you can say that work done is a positive, when the work done is going to be negative, and when the work done is going to be zero. We will discuss examination point of view. Applications based on this are very important. Now let us see. Now we will discuss here case 1. We'll discuss as a case 1, case 2, case 3. Okay, fine. Children, we will take examples. With the example only it will be very clear to us. For suppose children, here let us say it is earth only, earth surface, and let us the case of freely falling body. So freely falling body means body will be falling under the gravity like this. Okay, children, as the body is falling downward direction, can you please tell the direction of displacement? Obviously downwards only. So here body displacement, the body is displaced downward direction only. Children, in which direction the force of gravity will be there? Force of gravity will be downwards only. Now think once again. Don't you think that body is displaced in the direction of force? Yes, of course. Means displacement and force both are in the same direction. As both are in the same direction, children, what is the angle between force and displacement? It is 0. So in this case, theta is equal to 0 degrees. Children, we all know very well that cos 0 degrees is equal to 1. Children, these values we need to remember in order to understand the concept. Here mathematics is important. Clear? Fine. So let us recall the formula, children. W is equal to Fs cos theta. So here Fs cos 0 degrees, that is here Fs cos 0 degrees is equal to how much is 1. So finally we got W is equal to Fs. So children, here Fs you got positive or negative? Obviously the positive. So here work done is positive. Very important. So in exam they will ask you a question. When is the work done positive? It's very important. Children, when a body is displaced in the direction of applied force, then work is said to be done positive. So this is the first case where work done is positive. Now children, let us see the case 2. Let us see the case 2. First, suppose children, let us take the same case but a reverse. What is that reverse here? Look at here. This is case 2 where this is a case where body is thrown vertical upwards, children. Try to understand. But like this, let us take a marker. Body is thrown. Just to think that it is going continuously. It is going continuously. So obviously the displacement direction also will be vertical upwards only. Now whether body is moving away from the earth or towards the earth, children, the force of gravity direction is always downwards. So here this what actually the force direction will be downwards only. Now try to understand, both are opposite to each other. That is what, both are opposite. One is going like this, one other means one body is going along a positive y-axis, another one is going along a negative y-axis. What is the angle between positive y-axis and negative y-axis? This will be how much? It is a 180 degrees. So here theta is equal to 180 degrees. Now let us write the expression. W is equal to Fs cos 180. Fs cos 180 degrees. Children, cos 180 degree value is very important. Cos 180 is minus 1. So here W is equal to Fs into minus 1. So W is going to be minus Fs. That is what, children, here work done we got as negative. Work done we got as a negative. So when is a work done negative, children? When a body is displaced opposite to the direction of applied force. So here only examination point of view there will be a question. During the application question, let us discuss, children. During a cricket match, what we can say, the fielder catches a ball. In that process, work done by a fielder, is it positive or negative? Explain. They'll ask you a question. Children, obviously the work done is a negative. Think about it how. Children, in order to catch the ball, he has to stop first. Yes or no? Whether he pulls hands back or somewhere he has to stop the ball. For that, his hands should exert some force in order to stop it. It's very important. Means what? For example, let us take here is, children, it's not a snake, let us say it's hands. Okay, fine. So he has to apply the force. He has to apply force. And moreover, ball will be coming in this direction. Ball will come in this direction. Which means what here? Force and displacement both are in opposite direction. Then the work done is negative. Okay, children? Fine. And the case 3 is all about zero work done. Case 3. Let us see once again the case 3. So here, first let me discuss. For example, children, F is equal to 0. I mean what? If we are not applying force only, then can you say the work is done? No chance at all. So if force is 0, obviously displacement will be 0. Then work done will be 0. No doubt about it. Can you accept? Yes. Now let us take one more thing. Force is acting. Force is acting, but displacement is 0. Oh my God. This is a point where we should be a bit careful. Force is acting, but body is not displaced. Do we have an example? Children, the best example I will show you now. For example, let us take this board. Come on. Now I go on applying the force. Now I am going applying the force. I am applying the force. But do you think that this, what we can say, the board or the wall is displaced? No. Displacement is 0. Though force is acting, displacement is 0. When displacement is 0, obviously work done will be 0. Good catch. So work done will be 0. I am only saying that, good catch. But work done is 0. Now, it's very important, children. Force is acting on a body. I mean, it is not 0. Even there is a displacement. Still, can the work be 0? Which is very important. Children, listen here. Force is acting and the body is displaced. Is it do we have any situation where still work done will be 0? Let us take the case, children. Come on. So here is horizontal surface. Let us take here is some ball or anything, something. Okay, na? So this is going in this direction. I mean the ball is displaced somehow either left side or right side, what it may be. On this, children, still the force of gravity will be acting vertically downward direction. The force is acting, body is displaced. But children, what is the angle between force and displacement? It is 90 degrees. You may get one doubt. So what, sir? Theta is 90 degrees. So what? Let us think here. W is equal to, it is F as cos theta. Cos theta is what? Cos 90 degrees. Children, force into displacement into cos 90 degrees is equal to 0. Cos 90 degrees is equal to 0. 0 into something will be 0. So here W is equal to 0. So work done is 0. It's very important. Children, in these three cases, if you can notice, one common thing you should get. One common thing is there. What is that? Here, here, here. What? Work done by force of gravity. Children, it's very, very important. Whenever we are defining a work, children, you also should mention work done by which force. Here, work done by gravitational force is positive. Work done by gravitational force is negative. Work done by gravitational force is 0. So, children, it's very clear that work done can be positive, work done can be negative, work done can be even 0 also. And children, actually, this is a point where many students will get doubt actually. Many students will get doubt. That's what I'm telling you. You should mention the work done by which force. For suppose, children, let us take this body is thrown vertical upwards. Then you may get a one doubt. Sir, here work done by me is a positive because I am applying force vertical upwards, but body is displaced upwards only. The body is going upward direction. Work done is positive. Here you said negative. Yes, that's what I'm telling you. Work done by you. Again, in this case me. See, I am applying force. I am not thinking about gravity now. Gravity is acting downward direction. So, if you want work done by you is a positive because you are applying force upwards only. Body is going upwards only. But if you want to carry the work done by the gravitational force, it is a negative because its direction is downward direction. Children, these three cases I will try to explain with a single diagram so that you will get a full clarity. And before that, based on this, we have an application question that I want to discuss. So before that, just kindly just copy it so that we'll discuss one application. Then we'll go for one single diagram where we can understand these three cases when the work done is positive, when the work done is negative, when the work done is 0. These are the cases very, 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 very important. Okay. Can I raise? Yeah. So let me take out this case 2 so that one application, children. For suppose, let us take here is earth. Let us take here is earth and let us take here is satellite. You may take a natural satellite or artificial satellite, children, what it may be. So the work done, so we know that moon will be revolving around the earth. So what is the work done? In this case, work done is 0. Then 0. Many students will write 0 only. And how they will explain? They will explain like this. Sir, for example, moon is at a point A. Again, it will come back to the point A only. So the displacement is 0. So the work done is 0. Okay, it's correct only. But I am not talking only after complete revolution. No, it's not that. At every point, work done is 0. How it is possible? Yes, look at children. So for suppose this let us say this moon is at a point A. Here the centripetal force will be acting in this direction. Centripetal force. Clear, fine. And what will be the direction of a body which is in circular motion, children? Always along the tangent. I mean what? The body will be displaced. The displacement will be in this direction. So this is a direction of displacement. So here, what is the angle made, children? It is a 90 degrees. 90. Work done is 0. For suppose after some time, let us say the moon has come to this point. Point B. Still here also force will be, that is centripetal force, children, already we discussed. So regarding centripetal force which we discussed, Children, if you have missed that class, that link will be given in description. Kindly go through it because we should understand what actually centripetal force is. Fine. So, centripetal force. Again, the direction of displacement will be along the tangent. So, here also it is 90 degrees. Children, at every point, any point you can take, any point you can take. The force and the displacement are perpendicular to each other, so that work done is 0. Hope I am clear, children. So, based on the negative work done, the cricketer during the cricket match, work done is negative. That question we can expect. Whereas 0 work done, in this case especially, we can expect this application question. The work done on the moon which is revolving around Earth is 0, or satellite is 0. What is the reason? Reason is displacement is normal to the force applied. Clear? Fine, children. Now, as I told you that these 3 cases can be well understood with the help of single diagram. Single diagram, children. So that's what again I'm telling you, children. Whenever you are talking about the work, so you should mention which force is doing work actually. Then only you can decide whether work done is positive, work done is negative, work done is 0. Look at here, children. Okay. So for suppose, let us take here. Let me show my drawing skills now. Okay. Don't run away from. Okay, class. Just wait. Listen here. Okay. So here is, let me draw one vehicle. So, not bad. Not bad. Okay, fine. Let us just a car. Can you recognize which vehicle is it? It's car only. But don't ask me which company it is. Okay, it's a new. Going to make a new car. It is new company is going to come. Fine. So, it is a car. That's fine. Let us take that the car is in motion. Let us take a case where car is in motion, children. So, car is moving, so in this direction displacement will be. So here, this is how the car will be displaced. Children, as a car is moving in this direction, obviously the engine does some work. Yes or no? Obviously, engine will try to pull in a forward direction. I mean what here? Car engine applies force in this direction only, then only car will move, right? So this is a force applied by, what we can say, engine. Force applied by the engine. Fine. And children, as the car is in motion, don't you think that there will be a force of friction will be acting? Obviously, frictional force will be acting. Always opposite direction of displacement. And don't you think that, children, there will be a force of gravity will be acting here? Yes, force of gravity will be acting. So it's very, very important. See, the car is in motion. The displacement will be, let us say, positive x-axis direction. And on this car, how many forces are acting? 3 forces. Force by engine, force of friction, force of gravity. Now, children, let us see here, case 1 here. So, work done by the force of engine is positive. Why, children? Because the force by the engine and the displacement both are in the same direction. So, whenever force and displacement are same direction, work done will be positive. Okay, fine. Whereas, look at here, work done by frictional force, children, work done by frictional force. Body is displaced along the positive x-axis direction. Frictional force will be opposite to it. So, whenever body is displaced opposite to the direction of applied force, the work done will be negative. Work done will be negative. Let me tell you third case, children. Work done by the gravitational force is 0. Why? The displacement is in this direction. The force will be vertical downward direction. This angle will be 90 degrees. So this is how we can, that's what I'm telling you. Work done by which force are you talking is very important. In the same case, children, work done by the engine, that is the force applied to the engine is a positive. Work done by the frictional force is a negative. Work done by the gravitational force is 0. Hope I am clear. Just copy it. Then we will be discussing about the power concept. Now we discuss about the power. Children, power. So here, children, power is what? Nothing but the work done only. But we will talk in terms of time. So, to do a work, what is the time taken? So, based on that only, we will decide whether power is more or power is less. So children, what is the power children? Rate of doing work. It's very important. Rate of doing work is called power. Rate of doing work is called power children. So mathematically we can write power is equal to work by time. Power is equal to work by time. So if you want to apply for two cases children, we can write like this. P1 by P2 is equal to W1 by W2 into T2 by T1. Children, this formula we use in order to solve the numericals. Okay, now fine. Now look at here, it's SI units. Its SI units are joule per second. This joule per second we can call it the watt. W-A-T-T. The symbol can be a capital. But whenever we are writing the full name of the unit children, first letter must be a small only. The CGS unit is, it is erg per second. Erg per second. There is no name for this erg per second. You have to write like this only. And in exam they may ask you 1 joule per second is equal to how many erg per second? That is 1 joule per second is equal children, it is 10 power 7 erg per second. And children, power is a scalar quantity. Power is a scalar quantity children. It's very important. And even exam they'll ask you define the SI unit of power. I mean when you can say that power is equal to the 1 watt. Children, it's very important. Very important. For example, in order to do some work, that is, let us say we are doing a 1 joule of work. So this one, to do this 1 joule of work children, we have taken 1 second time. 1 second time. Then power is equal to 1 watt. It's very important. Power is equal to the 1 watt. Which means what? If 1 joule work is done in a 1 second, then the power is equal to the 1 watt children. So one, this watt is, we cannot use to measure the large amount of power, means, the watt will become very smaller. In that case, we can use kilowatt. Kilowatt is equal to 10 power 3 watt. And we also can use 1 megawatt. Megawatt is what children? 10 power 6 watt. If you want to measure very small amounts of power children, even we also can use 1 milliwatt. That is 10 power minus 3 W, or 1 microwatt also we can use, that is 10 power minus 6 watt. So other than this, we have practical units, very important. This is a very important examination point. What's a practical unit of power? Practical unit of power. In order to measure the power of engines, power of an engine of vehicles children, we use horsepower. So children, here 1 horsepower is equal to the 746 watts, or 1 kilowatt is equal children 1.32 horsepower. So examination point of view, these are very important. Fine. Okay. Now the very important thing is that children, very important. I mean, say it's very important. What is that? The factors on which power depends. So here children, power depends mainly on two factors. Mainly depends on two factors. The first one is work done. For example, children, two persons are there. We asked to do them work actually in the same time. Then obviously, whoever will do more work children in a given time is said to has more power. Which means what here? Power is proportional to the work done. Which means what here? To compare the power between the work done with the two persons, so we use this formula. So very important. It's clear? Fine. Even second one children, it also depends on time taken. For example, same task is given to two persons. Then whoever will do the work in a less time is said to has more power. Which means what? Less is the time, more is the power. Which means what? Power is inversely proportional to time taken. So children, here power is inversely proportional to the time. So this only can be written as P1 by P2 is equal to T2 by T1. So children, this is all about work, or we can say work and power. Children, now we will see how the numericals can be asked based on the work. We'll try to do at least one numerical based on work. and even how the numericals will be asked based on the power also we'll discuss. Okay children, fine. Just copy it. We'll go for one or two example numericals. So children, here is example numerical, we'll do it. Example numerical. First we do based on work children, based on work, then we do based on the power also. Okay, fine children. For suppose here is an object, let us say it is a body is placed, so that on this body children here, let us take 10 Newton force acting, 10 Newton force acting, so that body is displaced by, for example, 2 meter, such a way that the angle between force and displacement is 60 degrees, let us say 60 degrees. So in this case, look at children, here force is given 10 newtons, displacement is 2 meters, and the angle is 60 degrees. So the formula which we have, W is equal to, what is it children? Fs cos theta, Fs cos theta. Children, come on, use the formula, come on, use the formula, calculate, pause the video for that, just pause the video, just take the formula, substitute the values, just calculate how much answer are we getting. Children, come on, do it. Got it? Just comment your answer, then we'll see, come on, 3, 2, 1. Okay, so F is how much? It's 10, S is 2, this is cos 60 degrees. So this is 10 into 2 is 20 into cos 60 degrees equal to how much children? It is 1 by 2, that is 10 joules. So the work done is 10 joule. Clear? Fine. So let me one more question. Look at here. So here children, here is a body. Okay na? Sorry, it is a surface and here is a body. And here the force is acting in this direction, so that 50 Newton force is acting and the body is displaced by 10 meters, so that the angle is 30 degrees. Here I will give you hint children, cos 30 degrees is equal to root 3 by 2. Cos 30 degrees is equal to root 3 by 2. Come on, do it. Come on. What the answer you are going to get? Pause the video. So force is, let me tell you the question first of all. I gave you the data. Excuse me. Yeah, children, work done by the gravitational force. Work done by the gravitational force. Work done by the gravity. Come on children, pause the video, just try it. Got it? 3, 2, 1. Look at here. So here W is equal to, we know it is a Fs cos theta. F is what? 50. Displacement is 10. Cos 30 degrees is equal to root 3 by 2. 2 ones are 2 5s are 550 is 250 root 3 joules. Children, how many of you got correct answer? Got it? But children, this is wrong answer. This is not correct. Why? You may get confused. Sir, we substituted force value, S value, theta, you only gave you everything is fine. But children, try to understand. Work done by the gravitational force. I mentioned very clearly. In which direction the gravitational force will act? Gravitational force will be in this direction. So what is the angle here? Angle is going to be a 90 degrees. Children, already we discussed, whenever displacement is normal to the force, that is 50 into 10 cos 90 degrees is 0. 0 into something is 0. So work done is 0. Now it is correct. This is right. That's what I'm telling you. Whenever it is asked to calculate work done, so first we should think work done by which force? So previously it was correct when they will ask you work done by this. In this case, if they'll ask you just work done, but very clearly it is mentioned work done by the gravitational force. Gravitational force means no need to think. It always acts vertically downward direction only. So force of gravity and the body displacement both are normal to each other, perpendicular to each other. Then work done will be 0. Clear? So these are the two example numericals based on the work. Come on, just copy it. We'll solve the numericals based on power. Children, before going to discuss about the numericals based on power, children, here one important point we need to understand. See, sometimes children, work done can be stored in the form of potential energy. Of course, regarding potential energy we will be discussing. Just remember now. So then, if a work done is stored in the form of potential energy, so then how to calculate power? So children, we know power is equal to work by T. But if it is stored in the form of potential energy, it is going to be mgh by T. mgh by T. When you are talking about the work done by the gravitational force. Whereas, if the work done is stored in the form of kinetic energy, then we can use it is half mv square by T. Children, these two formulas are very important. Is it clear? Fine. So let us take one example here. So here example 1, that is based on the power I am telling you. So look at here, children. Question can be asked like this. So here is, let us say, staircases. Okay, na? Here is. So children, here let us say power person of mass, let us say 50 kg. 50 kg is climbing the staircases. For example, here 20 steps are there. Of course, here I have not shown in a diagram. Okay, na? Just 20 steps are there. And children, the height of each step is, let us say, 10 centimeters. 10 centimeters. To reach this point, the person, let us take, takes 50 seconds time. 50 seconds time. Then calculate the power of a person. Come on, children, try this. Come on, try this. Pause the video. Think about the data what is given. You have to do it and comment your answer. Clear? 3, 2, 1, go. So first let us read the data, children. Here mass is given. Yeah, g value, oh sorry, it is a 10 meter per second square only. Okay, if it is not given, you can take it as a 10 only. Usually it will be given in the question. So here mass is given 50 kg. Mass is given 50 kg and time is given 10 seconds. So this height, children, this is not given. This is not, we have to calculate. So children, it's very important. Number of steps into height of each step. This is going to be 200 centimeters. This can be a 2 meters. Clear? Now, so time is given anyhow, it is a 50 seconds. So here power is equal, children, we should use mgh by T formula. So here m is what? 50 into g is 10, h is 2 by 50 seconds. 50 cancel. 10 into 2 is 20. So this is a 20 watt. So children, this is how actually we can calculate the power. Is it clear? Just copy it. And we will do second numerical where they will ask us to compare the work done, compare the what we can say powers. Then we will take one more person also. Okay, children, fine. Copy this. I am going to change a little bit. Can I? Yeah, look at here. So this is, I will try to change into numerical 2. Look at here. Let me change this question a little bit. Same question, but I want to take for 2 persons. Okay. So it is the person A, let us say. Person A. From here, children, person B of mass 40 kg. Of mass 40 kg is climbing the same staircases. I mean, what height is going to be same staircases. For that, he takes for suppose 10 seconds. 10 seconds. So in exam, children, they will ask us to compare the work done and compare the power. Children, very important. Come on, compare the work done and compare the power. What is the question, children? Here, compare first one, work done, compare work done, and the second one is compare power. Compare power. Okay, come on children. So first, let us calculate the work done by both persons individually. Okay, so work done by A is mgh. So m is what children here? Mass of person A 50, g is 10. Displacement just we calculated. How much we got? H is equal to 2 meters, which we got is a 2. So this is going to be how much? 500 into 2000. So it is a 1000 joule. Now work done by person B also similarly. mgh mass is how much? 40. It is 10. It is 2. This is going to be how much? It is a 800 joule. Now what we have to do? We have to compare work done children. So work done by person A to the work done by person B is equal to, it is 1000 by, it is 800. Zeros cancel. 2 5s are 2 4s are. So comparison means we need to write the form of ratio, that is WA is to WB is equal to, what is children? 5 is to 4. So this is a ratio of work done. The second one, what they are asking us to calculate? Power they are asking us to calculate. So second one children, powers. So we know this, right children? What is that here? Power of a person A is equal to work done by person A by time taken by a person A. So work done by person A is how much? Work done by 1000. 1000 by how much time does it take? 50 seconds. 0 cancel. So power of a person A is equal to 20 watts. It is a 20 watts. Whereas power is equal for a person B. Okay, sorry, power of person B. Work done by power B by time taken by person B. So work done is how much? It is 800. How much time does it take? 10 seconds. 0 cancel. So power by is equal to what? It is 80 watt. So they are asking us to find the ratio, right? So power of a person A by power of a person B is equal to, so we got it as 20 by 80. 21s are 24 cities. So here power of person A is to power of person B is equal to 1 is to 4 is equal to 1 is to 4 children. So this is how actually we can expect the numericals. Okay children? Just the thing is that a concept is important. Understand the concept, then you apply so that we will get it. Just copy it. Now we will see for energy. Children, energy and work, if you can see actually, these both are relative terms. Which means what? If we are doing work means what? We have energy. If we have energy means what? We are able to do the work actually. So they both are relative terms. What is the energy children? The capacity to do the work. Which means what? If we have more energy, we can do the more work. If we have less energy, we can do the less work. That's what we can say, that energy is actually work done only, but we are talking the capacity. If we have more capacity to do the work, which means what? We have more energy. So the capacity to do the work is called energy. And as I told you that energy and work both are relative terms. So we will use the units, whatever we use, SI and CG units for what we can say work, we'll use for energy also. So here SI unit is what children? It is a joule, whereas CJ's unit is, it is a erg. Children, did you remember 1 joule is equal to 10 power 7 erg, or 1 erg is equal to 10 power minus 7 joule. Children, other than this, for example, energy means we have different forms of energy. Obviously, every energy has its own special unit. In that children, let us see 3 important energies here. The first one is heat. So this is what actually we have learnt already in a 9th class. Heat children. So heat is measured in calories. Then in exam they will ask you a question. How calories related to the joule? Children, did you remember? It's learnt in 9th class. Just think and just comment your answer. 1 calorie is equal to how many joules? Children, Did you remember? Come on, think. 1 calorie is equal to how many joules? It's very important. Or you also can try, you also can comment 1 joule is equal to how many calories also. Both are same only. So children, here 1 calorie is equal to 4.2 joules, whereas or 1 joule is equal to 0.24 calories. 0.24 calories. Fine. Okay. Next children, we are going to discuss the energy of the subatomic particles. Subatomic particles. Very important, such as proton particles, electron, neutron. If you want to measure the energy of the subatomic particles, children, we will use a electron volt. It's very important. Electron volt. So here electron volt. Let us see 1 electron volt is equal to how many joules. Here children, E represents what? Charge of electron. That is 1.6 into 10 power minus 19 coulomb, and volt is what children? Joule per coulomb. So coulomb cancel. So 1 electron volt is equal to 1.6 into 10 power minus 19 joules. Clear? Fine children. Now electrical energy. Children, regarding electrical energy, we will be discussing in detail in current electricity chapter. Here it is not required. So to measure the electrical energy, children, we use a unit called watt hour, kilowatt hour. Okay. So here 1 watt hour is equal to 3600 joules, whereas 1 kilowatt hour is equal to, very important, very important examination point of view, 3.6 into 10 power 6 joules. Okay children. So these are some special units of heat, energy of subatomic particles and electrical energy. And children, here in this unit we have one more point. What is that? Conversion of energies. Of course, which we have learned already, children. Learned is not in 10th class, in 9th class only, which we have learned already. Okay now. So conversion of energy. Children, we know very well that energy can be transferred from one form to another form. But in exam, they will ask you specially. For example, electric motor. What energy conversion will take place there? Electrical energy to mechanical energy. Electric bulb, electrical energy to what? Light energy. Electric heater, electrical energy to what? Heat energy. Photosynthesis, light energy to chemical energy. Dynamo, the generator will be there. Mechanical energy to electrical energy. Electric cell, when it is in use, children, chemical energy to electrical energy. But whereas cell during charging, electrical energy to chemical energy will be converted. What about loudspeaker, children? Loudspeaker, electrical energy to sound energy. Whereas microphone, sound energy to electrical energy. So dear children, like this we have so many energy conversions. You must read the textbook. In textbook, more than 20 energy conversions are given, which are very important examination point of view, because one mark question it can be asked. Okay na? Just copy this. We'll be discussing about the mechanical energy. Rotational kinetic energy. Children, this chart is very important. In a simple manner, we are going to discuss, children. Children, we know that every object has energy. It's very clear. So sometimes, the body may possess energy due to the rest, that is the position, and it may possess energy due to the change in configuration, due to motion, due to change in shape and size. So in all these cases, what are the energy possessed by an object is called what actually? Mechanical energy. So here mechanical energy is of two forms. It has mainly two forms. It is very important. Potential energy and kinetic energy. First, we will see what is the potential energy, children. So the potential energy, the energy possessed by a body by virtue of its size, that is a shape, change in configuration or change in position, is called what actually? Potential energy. The energy possessed by a body by virtue of what we can say position or a change in shape, change in size, change in configuration is called potential energy, children. Again here potential energy is of two types: elastic potential energy, gravitational potential energy. Children, first let us think what actually elasticity. Children, whenever you apply force on an object, his body, let us say it gets deformed, let us say that. But the moment when you can withdraw your external force, the body may regain its original shape and size. Such a bodies are called elastic bodies. That phenomena only we can call it as a elasticity, which means what? The property by virtue an object regains its original shape and size after removal of external force is called what actually? Elasticity. So, the potential energy gained by an object due to the deformed state, deformation might be in size or a shape, is called elastic potential energy. Clear? Fine. Come to the gravitation. So, this is due to the position, change in the position. Okay. This is due to the change in size or shape, that is a configuration. Fine. So, gravitational potential energy, children. For suppose, look at here. Here is a earth surface. Here is body of mass is there. This body is taken to a height, vertical height I am talking. Okay. Now, so that h is a vertical displacement. The moment when a body, a position is changed, it gains energy. Means here some work is done against the gravity. So, whatever the work is done is stored in the form of energy. That potential energy only we can call it as a gravitational potential energy. Then how to calculate, children? We know that here W is equal to force into displacement. Here force of gravity is mg, that is mg, and the vertical displacement h. So, this is the work done by the gravitational force. Work done by the gravitational force. Only we are talking about the magnitude here. Clear? Fine, children. See, and one more important point regarding the work done by the gravitational force, that is especially gravitational potential energy. For example, you are taking a body to a, means far from earth. I mean, you are taking somewhere you have taken to infinity. At infinity, children, at infinity, what will be the force of gravity? Force due to the gravitational earth, force of gravity, that is the force due to the earth, children? 0. So, at infinity, the gravitational potential energy is taken as a 0. Is it clear? Fine. Now come to the kinetic energy. Children, this kinetic word is derived from a Greek language letter called, it's a word called kynemo, sorry, K-I-N-E-M-O, kynemo. Kynemo means what? It's a motion. Kynemo means what actually? It's a motion, which means what? The energy possessed by a body by virtue of its motion is called kinetic energy. Children, motion means it can happen along a straight line path, it can happen like a to and fro, and it can happen a rotation also along the circular path also. So, based on that, kinetic energy is classified into 3 categories. Kinetic energy is classified categorized into 3 groups. One is translational kinetic energy, vibrational kinetic energy, rotational kinetic energy. So, if a body is going along a straight line path, the kinetic energy possessed we can call it as a translation kinetic energy. If a body is vibrating, especially molecules of the solid will be vibrating, then they are said to be possess what? Vibrational kinetic energy. Rotational kinetic energy. If a body is going in a circular path, it is in a rotational motion, then that kinetic energy, whereas that particular body has, is what actually? Rotational kinetic energy. Is it clear, children? Fine. So, these are the mechanical energy in a types. Examination point of view, they may ask you to define either of one here. Okay, na? Just copy it, and we will be discussing about kinetic energy and linear momentum. So, we discuss about a kinetic energy and how is it related to the linear momentum also we will try to discuss. Okay, fine. So, children, here for suppose body of mass m moving with the velocity v, children, then here kinetic energy expression can be written as kinetic energy is equal to half mv square. Half mv square. So, here based on this also, children, we will be having a numericals. So, here first, children, when velocity remains constant, here kinetic energy is proportional to the mass. That is, when they will ask us to be two bodies masses will be given, they will ask us to compare the kinetic energies if the both bodies are moving with the same velocity. So, we will use this formula. Fine. Even, children, if two bodies of same mass, that is mass remains constant, then kinetic energy is proportional to the square of the velocity. That is what here Ke1 by Ke2 is equal to V1 square by it is V2 square. One more very important formula which we will be having. Is it clear, children? Fine. And here, based on this one, we will get one question. What happens when a speed of a body is doubled? Then kinetic energy is increased by 4 times. It's very, very important. Is that clear, children? So this is all about actually kinetic energy. Now, how is it related to the linear momentum is very, very important. Linear momentum. So children, kinetic energy is equal to, we know it, half m v square. Let it be equation 1. And the linear momentum is equal to product of mass and velocity. From this, children, we can write v is equal to linear momentum by mass. Let it be equation 2. Now put this equation 2 in equation 1. Then what are we going to get? Kinetic energy is equal to half into mass into v square means what? It is p square by m square. Square m gets cancelled. Then kinetic energy is equal to p square by 2m. Children, it's very, 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 very important. Or we also can write P is equal to square root of 2am into kinetic energy. Either of one can be used. Okay, fine. And here one important point I am going to tell you. Children, as here kinetic energy is equal to P square by 2m. For suppose, children, example, here is a body of mass 2 kg. That is a body A. One more body of mass 10 kg. Let us say it's a 10 kg body B. Both will have same linear momentum. Then which body will have more kinetic energy? Children, it's very, very, very important. Which body will have more kinetic energy? Body has more mass. Body B has more mass. Body A has less mass. Children, pause the video. Think and comment your answer. Again, I am telling you. Two bodies of different masses but having same linear momentum. Okay, na? Then which of the two bodies will have more kinetic energy? Come on, think. Pause the video. Think. 3, 2, 1. Go. So generally, whenever masses are given and asked about kinetic energy, this relation will come to our mind. More the mass, more the kinetic energy. Less the mass, less the kinetic energy. If you think this relation, children, obviously you will say that body B has more kinetic energy, but that is wrong. Why it is wrong? Children, this relation holds good only when when velocity is a constant. But children, here nowhere velocity is mentioned. They are talking about a linear momentum, which means what? We should use this relation. So as linear momentum is a constant, kinetic energy is inversely proportional to the mass. I mean what? If more is a mass, kinetic energy will be less. Oh my god, it's very, very important. So every time you can't say that either kinetic energy is proportional to mass or inversely proportional to mass. No, it depends whether velocity remains constant or linear momentum remains constant. It's very important. When velocity remains constant, proportional to the mass. When linear momentum remains constant, inversely proportional to mass. So in this case, lighter body will have more kinetic energy. That is what? Body A has more kinetic energy than body B because the linear momentum remains constant. So this is how actually we have to think when we are even solving the numericals also. Okay, children, just copy it. Now children, we discuss the most wanted is work energy theorem. First children, how work is going to relate to the energy. Here energy means purely we are going to talk about kinetic energy only. Actually, one very, very important thing is that we cannot use the potential energy directly. It is just stored energy. If you want to use the potential energy, it has to be converted into kinetic energy. That is a very, very, very important. Potential energy is a purely stored energy. In order to use it, it has to be converted into kinetic energy. Okay, children. Now look at here. Let us say here is a body of mass m is going with some initial velocity u. And let children, the force is acting in the direction of motion. Obviously, if the force is acting in the direction of motion, obviously what will happen? The body speeds up. I mean what? The body velocity keeps on increasing. Let children, after covering some displacement s, let us say the body final velocity will be v, going to be v. As there is a change in velocity, obviously there will be a acceleration. Okay, na? Let us say that body is going with a uniform acceleration. What is wrong? Because the changes in velocity are a constant. Okay, no problem. Then you may get one doubt. Sir, what if the body, if the force acting opposite to its direction, then also there will be change in velocity. I mean what? Whether force is acting in the direction of motion or opposite direction, there will be a change in velocity. Children, whenever there is a change in velocity, there will be a change in kinetic energy. If the force is acting in the direction of motion, speed increases, so kinetic energy increases. If a force will act opposite to its direction, speed decreases, kinetic energy decreases. So this is what actually idea behind the work energy theorem. Work and theorem. So in this case, as there is a change in velocity, as there is some displacement is there, force is acting. Obviously, this force does some work. Let us calculate that work done, children, here. So here, work done is equal to F into S. Okay, let it be equation 1. But children, F is equal to, can we write MA? Yes, obviously we can write F is equal to MA. And from the equations of motion, we know that V square minus U square is equal to 2AS. Let it be, okay, 2AS. From this, children, let us write S is equal to V square minus U square by 2A. Let it be third equation. So here equation 2 and equation 3 we are going to substitute in a first equation. Then what we'll get here? W is equal to MA into V square minus U square by it is 2A. A cancel. Okay. So here work is equal to, children, what are we going to get here? M by 2 into V square minus U square. Now let us simplify this. We can write more in a simplified form. W is equal to half M V square minus half M U square. Now look at, try to understand this these words, individual children. So let us just recall about kinetic energy. What is the kinetic energy? Half into mass into square of the velocity. Here V is what? Final velocity. Here U is what? Initial velocity. So this term represents final kinetic energy. This term represents initial kinetic energy. So then it can be written as W is equal to final kinetic energy minus initial kinetic energy. So in this case, W is equal to change in kinetic energy, we can write change in its kinetic energy. So this is what actually work energy theorem. Work energy theorem. So how can we state work energy theorem? Children, it's very, very important. Work done by the force on the moving body in the direction of applied force is equal to the increase in its kinetic energy. Why I am saying increase in kinetic energy? Because speed is increasing. So obviously the change in kinetic energy also increases. For suppose if the force acting opposite to its direction of motion, then what will happen? The work done is equal to the decrease in its kinetic energy. That's what, children, in a, what we can say in a common way also we can write. The work done by the force on the moving body is equal to the change in its kinetic energy, which means what? Kinetic energy may increase, may decrease, depends on how the force is acting. If it is acting in the direction of motion, kinetic energy increases. If it is acting opposite to the direction of its motion, kinetic energy decreases. Is that clear? Just copy it. We will try to solve one important numerical, children. Come on, just solve. Just copy it. Is it done? 3, 2, 1, go. Children, very, very, as I told you that they may ask you the statement, they may ask you to write the mathematical form. What is that mathematical form? W is equal to half M V square minus half M U square. Fine. Now based on this, how the numerical will be asked, let us see. So example, children, example numerical based on this. So for suppose here, let us say it is a vehicle, a car of mass 200 kg, initially going with 18 km per hour, okay, and after 10 seconds, let us say its speed is increased to 72 km per hour. 72 km per hour. Then children, find work done, find work done, and also even power, Look at here, children. So here directly you cannot substitute the values, then you will get a wrong answer. Children, here mass is given how much? It is 200 kg. Initial velocity is given 18 km per hour. It has to be converted into meter per second. How? By multiplying with 5 by 18. So this is going to be 18 into 5 by 18 meter per second. That is 18 cancel. So initial velocity will be 5 meter per second. Whereas final velocity is going to be 72 km per hour. This is 72 into 5 by 18. 18 ones are 18 fours are. This is going to be a 20 meter per second. Anyhow, time is given how much? It is a 10 seconds. Now let us calculate first work done. So as per the work energy theorem, children, this will be m by 2 into v square minus u square. So mass is 200 kg by 2 into 20 square minus 5 square. This is 100 into 400 minus 25. This is going to be 100 into 375. This will be 37500 joules. So this is how we can calculate the work done. Then how to calculate the power, children? We know that power is equal to work by time. So work is equal to how much we got? 37,500. That is 37,500. Time is given 10 seconds. 0 0 cancel, then it will be 3750 watt. So children, this is how actually numericals can be solved based on the work energy theorem. Hope it's very clear. Just copy it. Now we discuss about law of conservation of energy. Children, conserve means what? Conserve means what actually? Constant. Children, as per the law of conservation of energy, it states that energy can be Now we discuss about law of conservation of energy. Children, come on. What is the law of conservation of energy? Let us recall. So according to this, energy can neither be created nor can be destroyed, but it can be transferred from one form to another form. Which is very, very important. So now we are going to prove this law of conservation of energy with the help of actually freely falling body. Even it can be explained with the help of simple pendulum also. Children, if what we can say, only the energy conversion is only between potential to kinetic and kinetic to potential, then we can write mechanical energy is equal to the sum total of kinetic energy and potential energy. So mechanical energy we can represent with the letter E, kinetic energy with a K plus potential with the U. So it's always remains constant. It's always remains constant. Which means what? Body may have potential energy, or body may have kinetic energy, or body may have both. But every point, if you can calculate the total energy, it always remains constant. But here conditions are applied. What is the condition? This is valid only when there is no air friction. It's very, very important. Very, very, very important. When there is no air friction, this you should mention. When there is no air friction, then only this is valid. Air friction should not be there. Okay, fine. So children, let us take a case of freely falling body. Here it is already made free fall. It is freely falling body. Let us say the body is like just it is a release from a height h, so that it is moving towards the earth. Children, let us take 3 cases. One is the initial point from where it is left. One is the point C, it's just about to touch the ground. It's actually in diagram to show it's touching, but it's just about to touch the ground. And B may not be a midpoint, children. Anywhere in between A and C. And here one important point, children. So initially at a point A, the body has 0 velocity. So it does not have any kinetic energy. As it is falling, after traveling the distance x, after reaching point B, it is at a height of h minus x, and it also has some velocity. Means what? At a point B, it has a potential and a kinetic energy. At a point C, children, it is just about to hit the ground. Means what? Height is negligible. As height is negligible, potential energy also negligible. So here whatever the mechanical energy it has, it's only in the form of kinetic energy. Now what we have to prove? We have to prove the total energy at a point A, at a point B, at a point C should be same actually. Look at each other. Come on. So first let us prove at a point A. Children, at a point A, as the velocity is 0, obviously kinetic energy will be 0. No need to discuss about it. And the potential energy is what actually? As it is a height h, the gravitational potential energy is going to be mgh. Then mechanical energy at a point A is what? The sum of kinetic and potential. That is what here we have to write as a mgh plus 0. It is going to be mgh. So children, at a point A, the body has the total mechanical energy is what actually? mgh. Now at a point B, let us see. Children, at a point B, it's very, very important. At a point B, the potential energy is how much? mg. But this body is at height of h minus x, because already it has covered x. Okay, na? So it is going to be mg h minus x. So this will be written as mg h minus mg x. This is the potential energy. Now kinetic energy is how much? Kinetic energy is going to be half m. That is, let us say it's not a v dash. Let us say it's a v1. At a point B, the velocity is a v1. So this is v1 square. But children, v1 value is not known. That to be calculated. Look at here. For that, we use v square minus u square is equal to 2as. So we are considering between point A to point B. So here u is 0. Here v is v1. The distance traveled is x. A is going to be g. Okay, na? Let us substitute the data. This is going to be v1 square minus 0 square is equal to 2gx. So v1 square is equal to 2gx. This value you substitute in this, then we will get the kinetic energy. So kinetic energy is equal to half m into 2gx. 2 gets cancelled, so kinetic energy will be mgx. So now let us calculate the mechanical energy at point B, children. For that we have to add kinetic energy and potential energy. Come on, this is going to be mgx plus mgh minus mgx. This will get cancelled, so energy at a point B is equal to mgh. Yes, we also got mgh at a point A and other at a point B. Now we need to calculate at a point C. So children, I need a space. Can I erase this? Hope you have copied. Yes. Let me take out this at a point C. So let us check at C. So at C means what? Body is falling from A to C. Here its initial velocity is 0. Here final velocity will be V. Total distance traveled will be H. A is equal to G. Clear? Fine. So potential energy at a point C will be 0, children. Why? Almost the height is negligible. It's just about to touch the ground. So kinetic energy will be half mv square. But here V value is not known. Again, let us apply the same concept, same formula we are going to apply. In the place of V, let us write the V square. Initial velocity 0 is equal to 2gh. So V square is equal to 2gh. So substitute this in this equation, then kinetic energy is going to be half m into 2gh. 2 gets cancelled, so kinetic energy will be mgh. Now let us calculate the total mechanical energy, that is the sum of the potential and kinetic energy. So total mechanical energy is equal to mgh plus 0. It is going to be mgh. It is at a point C. So children, which means what here? Whether you can take a point A or a point B, at a point C we got mgh only. Which means what? The total mechanical energy remains constant. But should not forget that when there is no air friction. So this is how actually we can prove conservation of energy. And children, here one important point, let me tell you. At a point A, the mechanical energy only in the form of potential energy. At a point C, the total mechanical energy only in the form of mgh. But at a point B, it is in the form of potential. Where is the potential? Potential and some kinetic energy. Okay, it's again the form is changing, not its magnitude. Magnitude remains same only, but the form which they possess is changing. Clear? Fine. Now same thing we'll try to discuss. So this is the last point in this chapter. Almost we are coming to the end. I think video is going to be 1 or 20 minutes or 1 or 30 minutes if I am not wrong. But still children, it's very useful to revise the entire chapter at a stretch. So children, here is let us take a case of here simple pendulum. So here is let us simple pendulum of Bob whose mass is m. Let us say OA is mean position, children. Now the moment we need to set it to the motion, children. Let us say here is given some velocity v. Then what will happen, children? Obviously it will be oscillating. To and from motion it has. To and from motion it has. To and from motion it has. Let us say it's a OB, it is OC. Okay, na? So it will be just oscillating. Okay, na? So such a way that children look at here. This, so that it will be its height is raised to height either of side. Here also height h only. Also height h only. Now it is very important, children. As it is going either towards B or towards C, this B or C called extreme ends. It's very important. Extreme ends, children. So after reaching this extreme ends, children, for a while it is stopped. I am not saying 1 hour or 2 hours it will be stopped. Just as it is going towards the point B and point C, which means it is going against the gravity, obviously speed keeps on decreasing, and at a point B and at a point C, its velocity will be 0. At extreme its velocity will be 0. So obviously its kinetic energy is 0. So it has a maximum height. Obviously whatever the potential energy will be mgh. So at extreme ends, the mechanical energy is only in the form of gravitational potential energy. Clear? Fine. Whereas at extreme end this is. So at a mean position, so some students here, they will have a confusion. Sir, at a mean position it is at rest, they will think. No, we are not taking that case. Already it is oscillating, but as it is crossing this mean position point A, it is going with the maximum velocity where it has minimum height actually. So at a mean position, as height is almost negligible, 0, so the potential energy will be 0, and it has maximum velocity. So the mechanical energy is only in the form of kinetic energy. Is it clear? Fine. And in examination point of view, children, they will ask us to calculate. For example, with if some velocity v, it is thrown, it is like it is pushed, to what maximum height is raised, or else what velocity to be given to the bob of the pendulum, so that it will raise to a certain height. So based on this, we will have a numerical. Children, based on the simple numericals, very, very important. So what I'll try to do is that next video, I'll try to discuss only exclusively just 3 numericals based on simple pendulum. It's going to be maximum 15 minutes video, but it's very, very helpful. So special video just I'm going to make so that you won't have any confusion, because the numericals based on simple pendulum are very, very important. I don't want in this video, so that that may not go into your brains actually. So special video I'll try to make, it's maximum of 15 to 20 minutes it will be. Okay, fine. So in this case, children, how to calculate the velocity v? So as per the law of conservation of energy, children, energy at a point A must be equal to energy at a point C, because we are neglecting the air friction. At a point A, it has only the form kinetic energy, that is half mv square. At a point C, mgh. So m cancel. So v square is equal to 2gh. So v is equal to square root of 2gh. So in order to raise the height of h, children, here what should be the velocity given? Square root of 2gh. If v value is given, g value is given, they will ask us to calculate the h value. Then h is going to be v square by 2g. V square by 2g. Is it clear, children? Just copy it. It's very, very important. Just copy it. Now, children, even examination point of view, as there is a exchange, between only potential and kinetic energy, how this mechanical energy is related to the height is very, very important. So this is the last point which I am going to discuss. Clear? So I want this space. So let me take this space. This is the last point. I think we need more 3 to 4 minutes to end the session. Okay, fine. So children, here mechanical energy versus height. Mechanical energy versus height we will discuss. So this is y axis. It will be, so height is taken on x axis, and energy, total mechanical energy is taken. So total mechanical energy at every point, at any point, should be mgh. It's very, very important. So this mechanical energy, whether height is more or less what it may be, it must be how much, children? It must be mgh only. Clear? Fine, children. Now as height is increasing, children, which energy is increasing? Potential energy. So potential energy will be increasing, and whereas which energy will be decreasing? Kinetic energy. Let us say from point O, let us say from Earth's surface, height is increasing. As height is increasing, so here one energy must increase. What is that energy, children? This energy is going to be a potential energy only. As height is increasing, potential will be increasing. Simultaneously, children, as height is increasing, kinetic energy will be decreasing. So this represents kinetic energy. Let me, this is a point where it is h by 2. This maximum height, let us say h, we have taken. So at h by 2, children, how much energy does it have, children? At this point it has maximum kinetic energy, that has maximum potential energy. But at midpoint, children, potential energy will be mgh by 2 only, kinetic energy also mgh by 2 only. Am I clear? So this graph is for a freely falling body, or you can throw body vertically upward direction, even you can take a simple pendulum. Okay children, fine children. So these are the concepts of chapter 2, that is a work, power, energy. I think maximum we try to cover almost all concepts. In between, one or two numericals we covered. Children, as I told you that the numericals based simple pendulum are very important. Okay, especially these numericals are related to the exercise 2C, if I am not wrong. So for that, as I told you that special video is made next 2 to 3 days, not more than that children. So as I told you that, yes, we will be uploading the videos in a regular manner, so that if you are following our channel, definitely it will be very, very helpful to you children. Okay children, again I am telling you, again, what is that? Yes, what you are thinking is right. You must read the textbook children. Textbook reading is mandatory. Kindly go through the textbook, try to make your own notes, and after that just you come back to the videos and watch. And children, one more thing, as I told you that we'll be discussing all numericals of all chapter. Each and every numerical will be discussed from chapter 1 to last chapter, whatever the chapters which we have, all numericals and even all exercise, that is the theory questions also will be discussed. So if you are following our channel children, 100% you will get the concepts, theory questions and numericals. Okay children, thank you so much, all the very best.